Welcome back. This is an Aleks homework video on calculating an equilibrium constant from a partial equilibrium composition. Okay, so if you are trying to find a K, you need to find the molarities of the products divided by the molarities of the reactants. So you're going to need a balanced equation to do that. So you're given here ammonia, and it burns with oxygen, and it produces nitrogen and water. Okay, so the first thing I would do is I would write an equation and then balance that equation. It's from the balanced equation that you're going to be able to use the expression or the equilibrium expression K sub C. So K sub C is going to be your products taken to the power of the coefficients multiplied together, divided by the reactants taken to its coefficient multiplied together. So N2 squared H2O to the 6 divided. Okay, so that's always the beginning. That's where we start. So we need to find the molarities of these. You're given the equilibrium molarity. No, you're given the amount of nitrogen gas at equilibrium. That's all you're given. So you don't know what this is going to be. This is K sub C equals. You don't know what this is going to be at equilibrium except for just the first one. So you're going to need to do an ice table. You're always going to do an ice table when you're trying to find something at equilibrium. So they tell you that you have 6.9 moles of ammonia gas. All right. So if you're going to have 6.9 moles and there's 100 liters, that's going to give you the 0.069 molar. And that is what the brackets mean. So when it says NH3 in brackets, you're going to take its moles divided by its liters, and that is the molarity. All right, so you're given the molarity of the ammonia, you're given the molarity of the oxygen. At the beginning, there is no nitrogen because it hasn't made any yet, and there is no water. So the products you're going to see is going to be equal to nothing at the beginning. Now here's the hardest part of this problem, and that's figuring out, essentially going back and doing your stoichiometry, what's getting bigger and how bigger is it getting? What's getting less and how much is it getting less? All right, so I'm going from back to the balanced equation, and I'm seeing that for every one of nitrogen, there's twice as much ammonia. Do you see? There's 4 ammonias and 2 nitrogens. So that means it's twice as much ammonia is going away as is being produced nitrogen. All right, so first of all, going away is going to give me a negative x. And if it's going away twice as fast as nitrogen is being made, then it's 2x. So it's minus 2x. I hope you can figure this out. Then the hard one would be the 3. Okay, so it is going away by 3 for every 2 that's being produced. So that is a 3-2 power. Okay, so take the 4 and the 2. That makes sense that it's twice as much. 4 divided by 2 is 2. That's twice as much. 3 divided by 2 is it's going away 1.5 times faster than the nitrogen's being made. So that's where I'm getting the 3. I'm getting the 3 from in front of the oxygen, the 2 from in front of the nitrogen. So it's going away, so it's negative 3,2. Now the nitrogen is being produced. That's your X. Okay, so think of it as that's what's being made is the nitrogen. And then how much faster is water being made than nitrogen? 3 times faster, because 2 moles are being produced of nitrogen, 6 moles of water. So that's your hard step. All right, so if you know that, then I'm just going to fill in the rest. 0.069 minus 2x, 0.17 minus 3 halves x, then nitrogen is plus x, and water is plus 3x. Now you're given 1.4 moles of nitrogen gas at the equilibrium. So I need to put that in molarity. Remember, that's not molarity, it's moles. Molarity is moles divided by liters. So 1.4 moles divided by 100 liters is 0.014 molar. Okay, and that's expressed with the brackets. That's what the brackets mean. So I just filled in 0.014 for each of the x's. Okay, we did this a couple slides ago. And we see that we've got numbers for each one. And I'm going to go back to the K sub C expression and simply fill in the 0.014 for N2, the 0.042 for water, etc., and then essentially fill it in with the same exponents as in the constant. And then I get 1.15 times 10 to the negative 4. It's 2 significant digits, so 1.2 times 10 to the negative 4. So involved, anything with nice table is involved. But once you learn that that's actually not the hardest thing you've ever done in your life, for whatever reason, when I did this the first time, I thought it was the hardest thing I ever did. It's not that bad. There's other harder things I've done since then, so maybe that'll give you some hope. But I hope you're doing well.